Welcome back to the Deep Dive. You know, when we think about critical infrastructure, aerospace, bridges, power plants, they all have this fundamental weakness, cracks. And usually studying failure is, well, reactive. We find a crack, then we figure out the stress.
Right. Is it safe now?
Exactly. But today, we're looking at something that flips that whole problem on its head.
Yeah, this is about moving towards prediction, using advanced intelligence, smart systems to get ahead of the failure curve.
That's the core idea. Our mission in this deep dive is pretty specific. We're digging into a research paper that uses machine learning algorithms.
Right.
And it uses them to predict the length of a crack.
Based on the stress data, the stress intensity factor, or...
Right. So it's working backwards from effect back to cause. This feels like a big deal for structural health.
It really is. And for you, the listener, think about structural health monitoring, SHM. This could be a huge shortcut.
How so?
Well, if you can reliably figure out the crack length just from stress readings, you get this generalizable, probably lower cost way to estimate damage early on.
Especially in things like thin-walled plates, like in aircraft.
Exactly. That's the focus here. The study uses theoretical Ceph data calculated using established methods, Tadaw's method, specifically for thin plates. Think like 1 millimeter thick.
Okay, so let's lay the groundwork before we get into the AI side of things.
Yeah.
Cracks in thin plates.
Yeah.
Why are they such a particular challenge?
Well, the main issue with thin structures is that failure often punches right through the thickness quite quickly.
Ah, okay. Not like a slow surface crack growing inwards.
Right. And how that crack then grows or propagates, that really defines the risk. Engineers usually break this down into 3 basic ways a crack can move.
The 3 fundamental fracture modes. Let's quickly recap those.
Sure. Mode I is probably the most common, or at least the most talked about. It's the opening mode.
Just pulling it straight apart.
Yeah. Pure tension, acting perpendicular to the crack surfaces. This one's often the most critical.
Okay. Then mode 2.
Mode 2 is the shearing mode. Think of the crack faces sliding past each other but staying in the same plane.
Like trying to cut something with really dull scissors, that kind of sliding force.
Exactly like that. The forces are parallel to the crack face in the plane of the material.
In mode 3.
That's the tearing mode. Or you might hear it called out-of-plane shear. This is more of a twisting action.
So one face moves up, the other moves down relative to the crack front.
Precisely. Tearing it.
Got it. And connecting all of these, mathematically speaking, is the key parameter, the stress intensity factor, SF, usually written as K.
Yes, S is absolutely central to what's called linear elastic fracture mechanics, or LEFM.
LEFM.
It basically quantifies the stress state right at the very tip of the crack.
So it tells you how intense the stress is at that critical point.
Exactly. Think of it like this. If K is low, the stress isn't dangerously concentrated. If K gets high, you're approaching the material's fracture toughness, and failure is likely.
And each mode has its own K value. TII, SDA, AIA.
That's right. Each describes the intensity associated with that specific type of loading.
Okay, now let's connect this back to the data in the paper. They looked at theoretical Ceph values for different crack lengths, from 5 millimeters up to 20. And when you compare the modes, one really stands out as the biggest threat, doesn't it?
Oh, absolutely. It's not just that Ceph increases with crack length in all modes. You'd expect that.
Right. Longer crack, more stress.
But it's the rate of increase. Mode 1, the opening mode, just takes off.
It accelerates much faster.
Dramatically faster. Looking at their numbers, for Mode 1, the Ceph value went from around 4.8 MPa square root millimeter up to over 22. That's more than a 4-fold increase over just 15 millimeters of crack growth.
Wow. And modes 2 and 3?
Much more gradual. Mode 2 started around 4.3 and only climbed to about 13.7. Mode 3 was even lower, ending up around 12.
So mode 1 is the dominant driver of failure risk here.
Without a doubt. It means if you're monitoring a structure, especially something thin-walled, you really need to be vigilant about those mode I tensile loads. That's where things can go from seemingly okay to catastrophic very quickly.
Puts a big target on K, right?
Definitely.
All right, so now the transition. Calculating K from a known crack length, A, is, well, standard engineering.
The X-book stuff, yeah.
But in the real world, you often don't know A. You can't just see inside the structure easily. You'd have to stop everything, take it apart.
Right, which is expensive and time-consuming. This is where the machine learning comes in, offering a potential alternative.
Because sensors can pick up signals related to stress, right? Things like acoustic emissions, vibrations.
Exactly. Those signals often correlate with the Ceph. The challenge is taking that noisy, indirect measurement of Ceph and translating it back into a concrete physical dimension, the crack length.
And that's what this study did. They flipped the script.
Precisely. They took calculated Ceph values for those specific crack lengths, 5, 10, 15, and 20 millimeters as the input data. And they trained these machine learning models to predict the actual crack length as the output.
Using the effect, the stress intensity, to infer the cause, the physical crack size. That's the core innovation.
That's it.
But you mentioned theoretical data. That sounds very clean, very perfect. The real world isn't like that.
It absolutely isn't. And the researchers knew this. If you train a model only on perfect data, it'll likely fail miserably when it sees real messy sensor readings.
So they had to make the data messier.
They did. They deliberately added noise to the theoretical Ceph values.
To simulate real-world conditions.
Exactly. Things like sensor errors, signal interference, environmental vibrations. They used additive Gaussian noise across 7 different levels of signal-to-noise ratio, SNR.
Going all the way down to 0 dB.
All the way down. 0 dB means the noise power is equal to the signal power. That's a lot of noise.
So if a model can work accurately even at 0 dB, it's incredibly robust. That's like trying to hear a whisper in a hurricane.
It's a serious stress test for the algorithms. It forces them to learn the underlying pattern, not just memorize clean data.
Okay, so which algorithms did they put through this stress test?
They chose 5 well-established regression models, specifically picked because they're good at handling nonlinear patterns and noise.
Makes sense. The Ceph to crack length relationship probably isn't a straight line.
Not at all, especially with noise. So they use support vector regressor, SVR,
Okay.
decision tree regressor, DTR, random forest regressor, RF extra trees regressor, ETR, and gradient boosting regressor, GBR.
Quite a lineup. SVR is good with boundaries, DTR simple, RF and ETR are ensembles, right? Combining lots of trees.
Exactly. RF and ETR are both ensemble methods using decision trees. They build many trees and average their predictions, which makes them generally robust against overfitting.
What's the difference between random forests and extra trees?
It's a bit technical, but extra trees introduces even more randomness when building the trees, both in sample selection and in choosing the split points. Sometimes this helps generalization.
Okay. And gradient boosting. That's also tree-based.
It is, but it works differently. GBR builds trees one after another, sequentially. Each new tree tries to correct the errors made by the previous ones. It can be very powerful, often yielding high accuracy.
Interesting. Now, one more detail on their method. They used regression models, predicting a continuous number,
Right.
but then mapped it to a classification. Why not just train a classifier directly to output 5, 10, 15, or 20 millimeter?
That's a really important point for practical SHM. You need the model to understand the continuous nature first, predict the actual length as best it can.
The fidelity.
Exactly. But then for decision making, the engineer needs a category. Is it small enough to monitor, maybe 5 millimeter? Is it needs closer inspection, 10 millimeter, or ground the aircraft now, maybe 15 or 20 millimeters?
So the discrete classes 5, 10, 15, 20 represent action thresholds.
Precisely. The regression gives you the detailed prediction, the classification maps it to the practical action needed. It's a smart bridge between mathematical output and operational reality.
Okay, makes sense. So time for the results. We have 5 algorithms, 3 fracture modes, lots of noise. Who came out on top?
Well, after crunching all the numbers, looking at the evaluation metrics.
Which were? Remind us.
Oh, right. They used mean absolute error, MAE, and root mean square error, RMSE, to see how far off the continuous predictions were.
Lower's better.
Lower's better. Then the R-squared score, RR, to see how well the model explained the variance in the data.
Closer to 1 is better.
Right. And crucially, the final classification accuracy. What percentage of the time did it put the prediction into the correct discrete bin, 5, 10, 15, or 20 millimeter?
The winner was?
Across the board, the most consistent and robust performer was the extra trees regressor, ETR.
Extra trees. What made it stand out?
It just hit the sweet spot. For example, looking at mode 2, which can be tricky, ETR got the highest classification accuracy, 85%.
Pretty good.
Very good. And it did that while also having a near-perfect R-squared score, like 0.993, and a really low average error, MAE around 0.31. It nailed both the regression and the classification parts.
Impressive balance.
Yeah.
But you mentioned random forest earlier. There was something interesting there, kind of paradox.
Yeah, the random forest, RF, is a great example of why you need multiple metrics. RF often looked fantastic statistically.
So,
It frequently had very high R-squared scores, sometimes up around 0.98, even 0.982 in mode I.
so statistically, it seemed to fit the data really well.
Exactly. If you just looked at R-squared, you might think RF was a top contender.
Right.
But its classification accuracy was often terrible, like down to 40% in mode I sometimes.
40%. That's worse than guessing. How can R-squared be so high, but accuracy so low?
It suggests that while RF's predictions followed the overall trend quite well, they weren't clustering tightly around the actual discrete class boundaries.
So maybe the real answer was 15 millimeters, but RF consistently predicted, say, 14.8 millimeter or 15.2 millimeter.
Something like that.
Oh.
Its predictions were close on average, leading to a good R-squared, but they kept falling just on the wrong side of the classification threshold.
Which, in a safety-critical application, is useless. Predicting 14.8 when the threshold for grounding is 15 means you miss the critical danger.
Precisely. It highlights that statistical fit alone isn't enough. You need the model to be reliable at those crucial decision points. ETR managed that much better.
Okay, that's a critical insight. What about noise, that real-world factor we talked about? How did the best models handle the simulated interference?
This was another area where ETR really shone, along with the gradient boosting regressor, GBR.
So GBR was also strong.
Yes, GBR performed very well too. Both ETR and GBR showed remarkable stability even when faced with high levels of noise, right up to that 30 dB level.
They stayed accurate even with tons of static.
Pretty much.
Yeah.
Their performance degraded much less than the other models as noise increased. That makes them really promising candidates for use with actual noisy sensor data.
And Random Forest, presumably, didn't fare so well with noise.
Not at all. RF consistently had the highest prediction errors, the highest MAE, across the noise levels. It just seemed much more sensitive to the disturbances.
Okay. One last finding mentioned was about which crack lengths were easier or harder to predict.
Right. It seems the models were generally most stable and accurate when predicting the mid-range crack lengths, the 10 millimeter and 15 millimeter classes.
Interesting. Why would that be?
The paper suggests maybe the SUF signatures for those mid-range cracks are more distinct, or perhaps the models had more balanced data around those points. The edge cases, the very small 5 millimeter crack and the largest 20 millimeter crack, showed a bit more prediction fluctuation.
Especially in mode 3.
Yeah, particularly in mode 3, the tearing mode. Maybe the stress field complexity at the extremes is just harder to pin down precisely, especially under those twisting forces.
Okay, so let's wrap this up. The main takeaway here seems pretty clear.
I think so. The study provides strong validation that, yes, you can train specific machine learning algorithms. ETR and GBR look like the stars to reliably estimate crack length from SIF data.
Flipping the problem successfully.
Right. And crucially, they can do this even when the input data is noisy, simulating real-world sensor issues. That's a big step towards a new tool for managing structural safety and longevity.
A powerful proof of concept. But, as always, there are limitations or next steps, right?
Absolutely. The big one stated in the study is the reliance on purely theoretical, analytical SUF data.
It's clean, calculated data, not messy measurements.
Exactly. It proves the principle mathematically, but the real test is yet to come.
Which brings us to the bigger picture. The future here is clearly about connecting this inverted ML approach with actual experimental data.
Or data from high-fidelity simulations like finite element analysis, SAF values derived from physical measurements, acoustic sensors, strain gauges, you name it.
So the provocative thought for you, the listener, is this. We've seen these models, particularly ETR and GBR, show remarkable accuracy and noise resilience using theoretical data. Now, imagine if they could maintain that level of performance when fed the complex, variable, sometimes messy data coming from real sensors on an operating aircraft wing or a bridge support or a turbine blade.
If that translation works.
If it works, how profoundly could that change everything? Think about mandated inspection schedules, maintenance downtime, the sheer cost and logistics of ensuring structural integrity in critical systems.
The potential to have a near-instant, non-destructive way to gauge damage severity. It could truly be transformative for safety and economics in fields like aerospace, civil engineering, energy, everywhere structural failure is not an option.
Something to definitely keep an eye on.